In this lecture, we discuss an advanced feature of HDF5, the ability to specify what layout you want for your dataset on disk. The choice of layout not only affects the efficiency with which you can retrieve data, but also permits you to use certain advanced features of HDF5, including data compression. HDF5 provides a number of storage layouts. By far, the most used are contiguous and chunked. Contiguous storage is the most common and the default you get for most datasets. It provides the highest possible speed performance for most access patterns, but does not support advanced features like compression. Chunk storage provides more flexible access and also supports compression and optimizations for unusual access patterns, and the ability to change the size of a dataset after it's created. HDF5 also includes more advanced layouts, including compact and external, which are good for particular situations. First, let's discuss contiguous storage. Again, this is the default storage mechanism for the vast majority of datasets. Keep in mind that all of these storage strategies are trying to achieve the same goal. Take an HDF5 dataset, which may be more than one dimension, for example, the 2D dataset we show here, and flatten it to a 1D array that can be stored as the bytes on disk. With contiguous storage, the approach is very simple. Elements along the last dimension are all stored together in the file, so access to that dimension is quick. For example, if we were to access row 1 of a particular array, that would correspond to a series of elements all lying near each other on the disk. It is much more efficient to access data that is close together on disk, and so iterating over the last dimension would be very fast. In contrast, we can imagine trying to access all the rows for a particular column. That would correspond to this kind of access pattern, and the corresponding elements would be spread throughout the entire dataset on disk. So, when using contiguous storage, it's important to keep in mind that all else being equal, access along the last dimension is preferred. Now, think about this access pattern. What if we wanted to access a tile of data? For example, the portion of data specified by the first 3 rows and the first 3 columns. This maps to a series of 3 blocks stored in the file, which are not contiguous. Unfortunately, there's no way to avoid this. Accessing data in a tiled fashion always results in access to the disk in separate locations. Chunk storage is a different approach to this technique. As an alternative to the simple approach of flattening the data to disk row by row. Instead, we divide our higher dimensional dataset. For example, here we choose chunks that are 3 rows by 3 columns, for a total of 9 elements per chunk. The chunk then becomes the atomic unit of access. So, that first chunk can be stored on disk all together. The next chunk, and the one after that, and the final chunk. So, if we were to read any one of these tiles, all the elements required to support that tile would be stored together in one location on disk. Chunks have many advantages. The one we just described is that they can optimize access if you've got a tile access pattern rather than a row or column access pattern. Importantly, we now have the freedom to store chunks anywhere in the file we want, not just one after another. So, we can apply various operations to them that can change their size. For example, if we wanted to compress them. And while contiguous datasets can't be easily resized, chunk datasets can simply be expanded by storing more chunks in the file. There are some trade-offs, however. Because data for each chunk is all stored together, reading or writing any data that falls within a chunk requires reading or writing of the entire thing. In this case, if we wanted to read 6 elements in a row from our dataset, because that data intersects with 2 chunks, we are required to read both chunks from the disk. In other words, we only wanted to read 6 elements, but we are required to read 18 elements or 2 chunks from disk. Let's see an example of how to use chunks with H5Py. Let's imagine we wanted to store 100 images, which have a size 640 by 480, and we knew ahead of time that our application would access them in 320 by 240 tiles. In other words, 4 tiles per image. We'd make a new dataset with shape 100 by 640 by 480, and then specify, via the chunks keyword, the shape of 1 by 320 by 240. In other words, each chunk will have a dimension of 1 along the image axis from 0 to 99, 320 along the x-axis, and then 240 along the y-axis. The important thing to remember is that whether or not a dataset is chunked, we still use the same NumPy slicing techniques for access. Here, we can read the first tile by specifying we want the first image, and then region 0 to 320 and 0 to 240. Although not required, access along tile boundaries will be very fast. For example, this access pattern, retrieving 1/2 of the first 3 images, is also aligned to tile boundaries. Of course, we're perfectly free to use whatever slices we want, keeping in mind there may be efficiency trade-offs. For example, this slice retrieves one small portion in the center of the image, which happens to hit the boundaries for all 4 tiles. So, although we retrieve a very small piece of information, we're required to load all 4 tiles from disk. Here are some things to keep in mind when using chunking. First of all, HDF5 needs to record some information on disk to keep track of the chunks. So, making too small a chunk size tends to take lots of disk space and to lead to slow performance, as HDF5 has to figure out which chunk to load. Very large chunk sizes prevent HDF5 from doing caching. And of course, if you need to retrieve only a few elements, being required to load a very large chunk is a bad idea. Generally speaking, you should try to keep the chunk sizes between a few tens of K and a few hundred K. As always, you should experiment and see which approach works for you. Let's discuss one very important application of chunked datasets, the ability to make your datasets resizable. Ordinarily, the size of a dataset is fixed when it's created. For example, if we create a dataset with shape 1000, that dataset will always have 1000 elements, no matter what. But if we use the max shape keyword to create dataset, HDF5 will permit this dataset to be enlarged all the way up to 5000 elements. Having created the dataset, we can retrieve the shape. As specified, the current shape is 1000, and the maximum shape, or max shape, shows 5000 elements. Now, we can use the resize method, specify the new shape we want, and HDF5 will resize our dataset. We can also make the dataset smaller. In this case, we resize it to size 500. Keep in mind that unlike NumPy, when you shrink a dataset, any data in the elements which are thrown away is lost forever. You can also make a dataset resizable with no limit. For example, in this case, we have created a dataset that has shape 100 by 8000 and specified a max shape of none at 8000. That means the second axis is restricted to be 8000 elements long, but the first axis can have any size. For example, we can resize it to be 1000 by 8000 or to be 1,000,000 by 8000. HDF5 permits either one. Behind the scenes, HDF5 is using chunked storage to make the dataset resizable. Here are some guidelines on how to choose appropriate shapes for your chunks. The most important rule is to always try to match the chunk shape to the access pattern you expect. Keep in mind that your chunks can be any shape you want, including one-dimensional chunks for one-dimensional problems. If you want to use extensible arrays, in most cases you're required to use chunked storage. You may have noticed that in the previous example, we did not specify a chunk shape. This is because the H5Py package can pick a chunk shape for you if chunking is required. Unfortunately, since H5Py has no idea what your access pattern is, the shape it picks may not be optimal. To summarize, chunk storage enables features like resizable datasets and compression, and is also excellent for access patterns that don't mesh with traditional contiguous storage. And in general, you should be careful when picking the shape for your chunks, as it's important that it matches your access pattern. To learn more about advanced techniques for storage, including compact or external storage, consult the HDF Group website at hdfgroup.org.